This webcast looks at worksheet 6A, where there are several examples of problems that involve friction force. So in the first problem, we're talking about a sled that has a weight of 300 newtons. It's moving at a constant speed over a horizontal floor, and there's a force of 50 newtons being applied to push the sled. So let's do a force diagram. So the sled has a weight, which means its gravitational force, it's being exerted on it by the earth, is 300 newtons. It says there is 50 newtons of applied force. I'll just say by a person. And so that's 50 newtons. We're talking about friction, and so I'm going to put in a friction force. And of course, the floor is supporting the weight of the sled, and so that's a normal force on the sled by the floor. Now, in this particular case, I know that it's moving at a constant speed. And so that is a clue to tell me that the net force in the horizontal direction is equal to 0, right? By Newton's first law, if something is moving at a constant velocity, then the net force is 0. Okay, and in the horizontal direction, I would add those forces by saying it's equal to the applied force minus the friction force. So that tells me that the friction force has the same amount as the applied force, which is 50 newtons. Okay, so I'm going to go ahead and label that. And since the sled is not moving up or down, the net force in the vertical direction is also 0. And so the net force in the vertical direction is also 0, and that equals the normal force minus the gravitational force. Because of that, I know that the normal force is the same amount as the gravitational force, which is 300 newtons. So I can label my normal force. So therefore, I know that the normal force and the gravitational force are balancing each other, and the friction force and the applied force are balancing each other. So now it's asking me to find the coefficient of kinetic friction between the sled and the floor. So I'm going to start by writing the relationship between the kinetic friction force and the normal force. The kinetic friction force equals the coefficient of kinetic friction multiplied by the normal force. And so here I'm trying to solve for the coefficient of kinetic friction, and so I'm going to divide both sides of this equation by the by the normal force. So that's going to equal the ratio of the kinetic friction force divided by the normal force. Well, I know now that the friction force is 50 newtons and the normal force is 300 newtons. Do you see that the newtons are going to cancel, and so my coefficient will be dimensionless. It won't have any units on it, but it's going to be 0.167. Okay, let's go ahead and look at another one. Oh, let's look part C here. What would the acceleration be on the sled if the coefficient was 0? The coefficient being 0 basically means there is no friction force, right? So if there were no friction force, we would just have the applied force in the horizontal direction. So the net force in the horizontal direction would now be the applied force, which is 50 newtons. And we know Newton's second law says that acceleration is the net force divided by the mass. Let's see, do I know the mass? I don't know the mass yet. I know the weight of the sled. So the mass of the sled is its weight, 300 newtons, divided by 9.8. And so that is 30.612 kilograms. Okay, so the acceleration would be the 50 newtons of net force divided by the 30.612 kilograms of mass, which would be 1.633 meters per second squared. Okay, let's go on to number 2. Here we've got a 1 kilogram lab mass. That's this little mass that's hanging off the table, and it's attached to a 4 kilogram block. And so, and notice that it's attached by this string that runs over a pulley. We did a lab similar to this. So the weight of the 1 kilogram mass is an unbalanced force that pulls the block across the table. Okay. And so now that we understand that, let's do a force diagram for the block. That's the green block, right? That's the block. So let's see here. Here's the block. So I have the weight of that block, the gravitational force, is its mass, which is 4 times 9.8. So that's 39.2 newtons. It's being pulled by the string, and the string has a tension force which is equal to the weight of that 1 kilogram lab mass. And so that would be 1 kilogram times 9.8. It would be 9.8 newtons. Let's see. There's probably some friction on this table. Now in this problem, they're not telling me that the block is moving at constant velocity, so I don't really know yet what that friction force is. But we'll just label it. And I know that there's a normal force. The table is supporting the block. And since the block is not moving up or down, I know that the net force in the vertical direction is equal to 0. That means that the normal force and the gravitational force are balancing each other. So I know the normal force in this case equals the gravitational force. Okay, so that's our force diagram. It says what would be the minimum value of the coefficient of static friction for the block to remain motionless. So motionless would mean that the net force in the horizontal direction would be 0. And I would find the net force in the horizontal direction as the tension force minus the static friction force. So in other words, the static friction force would have to be something bigger than, would have to be at least as big as the tension force. Okay? And the static friction force is the coefficient of static friction multiplied by the normal force. Okay, and I'm trying to solve here for this coefficient of static friction. So the coefficient of static friction would be, sorry, let me keep my inequality here, would have to be greater than or equal to the ratio of the tension force divided by the normal force. Well, the tension force is 9.8, the normal force is 39.2, and so I get 0.25. If the static friction is at least as big as the coefficient of static friction is at least as big as 0.25, then the block will remain motionless even though that little lap mass is pulling on it, on that string. Well, so then, this is a new problem really, part C. It says, okay, the coefficient of static friction is 0.2. Okay, so that's smaller than the minimum to keep it still. So it's probably going to move now, right? The block will move. It will slide because the applied force is bigger than the maximum static friction force. Right? The applied force is 9.8, and that's bigger than the 0.2 times 39.2. (9.8) is larger than 7.84. Okay, so the block will move. So now that we know it will move, we want to use the kinetic friction to find the acceleration. Right? You only have one mode of friction at a time. If we do not have static friction, because the block is sliding, we have kinetic friction. So the kinetic friction is going to equal the coefficient of kinetic friction times the normal force, which is 0.18 times 39.2. which is 7.056 newtons. So the net force on the block would be the applied force minus the kinetic friction force. And so that would be 2.744 newtons. And now I use that net force to find the acceleration. The acceleration would be the net force divided by the mass. By the way, if we look at this diagram, both the masses, the block, which has 4 kilograms of mass, and I've highlighted that green, and that lab mass that has 1 kilogram mass that I've highlighted yellow, they're tied together by this string that connects them, and so the total mass that accelerates is the sum of the two of them, right? They're tied together, and so if the green block is sliding across the table, the yellow block is falling toward the 4, and so the total mass would be 4 kilograms plus 1 kilogram. Okay, so when I calculate the acceleration, I have to use the total mass. So it would be 2.744 newtons over the sum of the 4 plus the 1 kilogram. And so we get an acceleration of 0.549 meters per second squared. Okay, let's go on and do number 3. We've got a classmate, standing on the floor, and someone pushes him with 100 newtons of force, and they're giving me the kinetic friction, the coefficient of kinetic friction. So let's do a force diagram. So the classmate has a weight, and her mass is 50 kilograms. We multiply that by 9.8. Her weight is 490 newtons. Someone is pushing her, so I'm going to call that an applied force. They're pushing her with 100 newtons of force. They're giving me a coefficient of kinetic friction. So I know that the kinetic friction force on the girl by the floor would be the coefficient of kinetic friction multiplied by the normal force. Let's see if I can figure out the normal force. The floor is supporting the girl. Since there are only 2 forces in the vertical direction and the girl's not moving up or down, I know that the normal force is balancing the gravitational force, so it is also 490 newtons. Okay, so the friction force is 0.15 times 490, which is 73.5 newtons. Okay, so now it's asking me the acceleration. To find the acceleration, I need to find the net force in the direction of motion. We're talking about the horizontal direction, right? She's not moving vertically. And so the net force would be the applied force minus the kinetic friction, which would be 100 newtons minus 73.5 newtons, which would be 26.5 newtons. So if I know the net force on the student, I can find her acceleration. It would be that net force divided by her mass. And so I've got 26.5 newtons, and her mass is 50 kilograms. And so we get 0.53 meters per second squared as her acceleration. Part C says, okay, suppose this girl is resting on carpet where the coefficient of static friction, this is talking static friction, is 0.25. Is that 100 newtons of horizontal force going to be enough to cause her to slide across the carpet? Okay, so, we're talking about the same weight. She still has a weight of 490 newtons. That is still the normal force. The applied force is still 100 newtons. But now we're, I don't know why I got yellow there. Let me erase that. Now we have, now we have a friction force, a static friction force, which is 0.25 times the normal force of 490. It's 122.5 newtons. So since the applied force is less than the maximum static friction, the girl will not slide. Across the carpet, right? The static friction force is large enough to balance the applied force. And so the applied force is not going to be enough to overcome that static friction force. Let's go ahead to number 4. We have a bartender pushing a glass down a wooden bar. And so the glass weighs 7.35 newtons. They're giving us the initial speed, and the force of kinetic friction opposes its motion, and it stops after 3.1 seconds. Okay, so let's see here. The weight of the glass they gave me. It's 7.35 newtons. There is no applied force. We're looking at it after he has pushed it. So it's sliding, but there's no hand pushing the glass, okay? So there's no applied force horizontally here. But there is a friction force, and it's going to be a kinetic friction force because the glass is moving on the glass by the bar. And let's see, and the bar is supporting the glass, so there's a normal force on the glass by the bar. It's going to be the same as the weight because I only have the two forces vertically, and I know the glass is not moving vertically. So in this case, the net force is to the left, right? There's nothing balancing the friction force. That means there's an acceleration to the left, okay? Which means it's slowing down, right? The glass is moving to the right, but the acceleration is to the left. And since they're in opposite directions, I know that the glass is slowing down. Okay, so I think that we're going to have to find the acceleration, and I'm going to use a kinematic equation for that. So let me make a list of the things that I know. I know that the initial speed is 1.25 meters per second, and I know it stops. So the final velocity is 0, and it stopped after 3.1 seconds. So I'm trying to find the acceleration. The definition of acceleration is the final minus initial velocity divided by the time. I'm going to use that equation. And I get a negative 0.403 meters per second squared. So that's good that I know the acceleration. I really need to find the kinetic friction. So I'm going to use the process where we find two equations to find the net force. One of them is Newton's second law. Net force is mass times acceleration. The other is looking at my force diagram. In this case, the net force is the negative of the kinetic friction force. And okay, so the mass, do I know the mass of the slide? of the glass, I don't know that yet, right? They gave me the weight of it, so let me find that. The mass of the glass is 7.35 newtons divided by 9.8 meters per second squared, which is 0.75 kilograms. Okay, so I know that I've got 0.75 kilograms times an acceleration of negative 0.403, and that's going to equal negative the kinetic coefficient of friction multiplied by the normal force, which is 7.35 newtons. And of course, I'm solving for this coefficient of kinetic friction. And so that's going to be 0.041. Okay. And then they're asking me how far the glass will travel before it comes to a stop. This sounds like another kinetic equation, right? So let me make a list of what I know. So again, I know the initial velocity, I know the final velocity, I know the time. Now I know the acceleration. I can really use any equation I want that has delta x in it. So I'm going to use the fourth equation. The displacement is half the sum of the initial plus the final velocities multiplied by the time. And so it's going to slide 1.938 meters down the bar.